All right, welcome back from the break. Sorry about that. CS4510, L15B. The topic of today is NP, which you're not going to believe this, does not stand for not polynomial, but non-deterministic polynomial time. So what is non-determinism? I mean, we already did this. We talked about non-determinism in the context of an NFA, in the context of a PDA, in the context of a non-deterministic Turing machine. We'll call it the deterministic Turing machine as transition function of the form. It takes as input a single symbol, it takes a state and a symbol pair, and it, wait, am I getting this right? It, from some state, read a symbol, move to a new state, write a symbol, and then move left to right. That sounds right. But the non-deterministic Turing machine has this non-determinism branching going on. So what it does is it adds some state, read a symbol, move to a sequence, a set of state symbol left-right pairs, right? Effectively, if you are, let's say at this state QI, you can either read an A, write a B, and move left, or maybe you could read an A, write a C, and move right. You're allowed to have transitions like that in a non-deterministic Turing machine, right? In some sense, it can effectively guess the computation. You measure non-determinism as, with n time, f of n, to be exactly what you think it is. A non-deterministic Turing machine accepts that language in f of n steps. Now, in some sense, the runtime, the different models of computation are really just different ways to measure time. Because you measure the time complexity of a non-deterministic Turing machine effectively as the depth of the computation tree, but not the number of branches or something like this, right? Because you allow the machine to make quote-unquote lucky guesses, where it accepts that there exists a computation that accepts, right? So whatever the length of that computation is the number of steps. So that's just one path in perhaps a large tree of computation. So it's effectively the depth of the computation. That's a different way to measure time. If you had to guess, what is NP?
The union of n time.
Okay. That's not the definition we learned of NP in 3510. What is the definition of NP we learned in 3510?
Verifiable in polynomial time.
We'll prove those two are equivalent. Let NPV, we'll see, be the class of languages that are verifiable in polynomial time. The way I'll write this is we could say that W is in L, if and only if there's a polynomial time verifier for it, right? So what we would say is that there exists a witness X of polynomial size such that V on W comma X accepts in polytime. So a problem is said to be in NPV if it is verifiable in polynomial time. This is a deterministic definition. This is the non-deterministic one, right? So let's read this definition real quick. There exists a string X of polynomial size, and this is notation, we won't use this more too often, I just want to do it once so you know this. The witness must be polynomial size, and there is a machine that can be convinced by such a witness. In the sense that if there is a solution, there is a short response that the machine can take as input that will convince it of this. For example, SAT is in NP because you can easily convince someone that a formula is satisfiable. We'll review SAT later, but you can easily convince someone of an answer sometimes, right? You just have to tell them what the answer is. So in some sense, the verifier is kind of like an autograder, except it's not grading the answer X, it's grading the problem, right? But this is the definition of NP as we learned in 3510, a verifiable definition. It turns out, as you may guess, these definitions are equivalent. The 3510 definition exactly and only corresponds to the notion of non-determinism as it exists in 4510. Let's prove it. How do you prove two sets to be equal?
Double set containment.
We're going to do a double set containment. Pick a direction. Which one do you want to go to first? That one and that one, or that one and that one?
The first one.
That one and that one.
Yeah.
We prove NP is a subset of NPV. So let L be an NP. So there is an NTM, let's say N, to decide L in n to the k steps on all inputs of size n, right? We give polytime verifier verifier V to decide L. So V is going to take as input W, and then it's also going to take as input this witness X. Whenever you do a proof in 3510 that a language, a problem is an NP, you decide on the verifier, right? You also decide what the data structure of the witness is, or the certificate, right? What does it encode? To prove SAT is an NP, the witness is the satisfying assignment. To prove clique is an NP, the witness is where the clique is in the graph, what the actual clique is. What should our witness be? We need to make a decision on that. And recall, basically, every time we do these kinds of proofs, remember when we did the 2 tape on the 1 tape and so on? All we really did was simulate the machine. So this is a verifier that's going to simulate the machine in some way. So first we're going to say, but the problem is it's deterministic, and this is a non-deterministic machine. So here's what I'm going to say. Simulate n on W deterministically. That almost works, but if you recall, we mentioned that the deterministic simulation of a non-deterministic machine did BFS. Do we remember this? That was exponential time in the depth of the thing. So that's actually an exponential time. We want a polynomial time verifier. If this runs in n to the k steps, right now this runs in 2 to the n to the k steps because it has to do this big thing. So this is not a polytime verifier right now. But we have, importantly, the difference between a polynomial time algorithm and a polynomial time verifier is this x. And this x, although it seems like just something to be thrown away, it's a single string, it is a very important thing, is given to you by God. It is all the answers to any questions you could ask. So if we need to simulate n on W deterministically and we are faced with a difficult choice, we need not compute for it. We may simply ask for the answer and be given it. The same way that we have by proving this double second containment, we're basically proving that who has a lucky coin actually has this alternate timeline thing. Those are in some sense identical. If we are faced with a non-deterministic choice, if faced with a non-deterministic choice, simulate on one branch. I'll say choose the branch to simulate using next bit of X. So the witness, what I'm saying, encodes the sequence of non-deterministic choices. If a non-deterministic machine may make several deterministic choices and also several non-deterministic choices. The non-deterministic choices can be encoded as a bit, 0 or 1, right? Which one do you make at that step? So in some sense, X encodes the polynomial time computation history, non-deterministic parts at least, of the non-deterministic machine on W, right? You can simulate n in polynomial time by every time you need to break a tie, essentially, instead of searching on both branches, you search on one by using the bit of C to tell you which way to go, the bit of X, excuse me, right? Do we agree that works? Is this sufficient for us to conclude that L is an NPV? You can verify a non-deterministic computation where the witness is what the non-deterministic choices were. Questions on that? Yes.
How does X look in terms of W, or is it just completely separate?
Yeah, that's a good question. X is, the way you would read something like this is that there exists an X such that V on W accepts. As in, this machine on input W can be given an X to convince it to accept W. In the sense that there's a short proof of something. Like X you can consider to be a proof. You can quickly convince someone of an answer. That's what it is. And X actually will be a function of W. But when we phrase it like this, what we mean is like, it is in fact
difficult to compute x as an algorithm. It is difficult for you to actually find x. We don't actually know what x is. That's okay, because if it does exist, we can verify it. But we don't actually know if it does exist. But if it did, we could verify it. That's what we're saying, right? We don't actually know if n accepts w or not. But if someone could tell us if it does, we could be convinced that their answer is correct. Yeah. There's only one other way to do it. Let's do the reverse. Let's prove that all verifiable computation can be non-deterministically accepted in polynomial time. So let L be in NPV. So we know that W is in L if and only if there exists a witness string X such that V on W X accepts in polytime. We give n, and let's even say, forget polytime, let's even be more specific. Let's say for some k, some n to the k time, okay? We give polytime NTM n to decide L. N on input W should do what? It doesn't have access to X. Right now it only has access to W. But it does have non-determinism.
Should decide.
Yes, I agree. Somehow it needs to determine if X, so the only thing we know is that there's a verifier for L. N, I'll give you a hint, wants to simulate the verifier in some way. The problem is the verifier needs W and X. We have W, how do we get X?
Because it's non-deterministic, it's built in almost. You can kind of,
Say a little bit more. You're almost there.
so the NTM, instead of having to choose which branch, it does the branch that's right, because it's non-deterministic.
Yes. I'll tell you the way we can word this for an algorithm. Non-deterministically, guess an x of size at most n to the k, simulate v on w comma x. So two things. One, the non-determinism can be front-loaded. In the sense you do all the non-determinism at the beginning, and then you just do deterministic simulation. You use non-deterministic guessing to just guess the witness. For example, why is SAT in NP using this definition? Just guess the satisfying assignment. What do we mean by guess? We use this terminology guess, but what we really mean is branch non-deterministically for all possible witnesses. So in some sense, if you were to look at the computation tree, there would be a n to the k branches for each possible bit of strings of length n to the k. And each of those branches would correspond to, I guess in my head, it would look like this. Not the NTM, but the computation tree of the NTM. I'm not good at drawing a fast binary tree, but, right? So this part would be non-deterministically branched for all possible witnesses. And then for each of those, you just run the deterministic simulator, right? Does that visually make sense, maybe? So just guess the verifier, and what it really does is it doesn't do all these branches simultaneously. It chooses the correct branch through lucky coin flips or whatever, and then just runs only that one. Now, if the witness exists, the non-deterministic verifier will guess it. If the witness does not exist, then it cannot guess it. So the simulation will fail. So if the verifier should accept W given to be convinced by X, the non-deterministic machine can guess X to simulate the verifier. If no such X exists, then the NTM cannot guess it. Now, why is this important? This is a big exists sign, okay? That's very, very, very important because non-determinism is existential. Those are essentially the same. What is the definition of an NP machine? It accepts if there exists a computation, and it rejects if all computations reject. Same thing. A verifier accepts if there exists a witness, and it rejects if all witnesses cannot convince it, right? So NP is characterized well by its existential banner. The definition of NP and by the way, we've done the double second statement, so this proves NPV is equal to NP, right? But both these are, in the simulation for both of them, important is the fact that the exists part of one simulates the exists part of the other, right? They are in some sense the same. Questions on that proof?
Less on the proof, but just to make sure I understand, the difference is basically like more of a formatting thing, where the non-deterministic part is either an X or it's created, or
Yeah, so like when you have a class and you prove them to be equal, the difference between them mathematically is not so important depending on how you measure it. For example, we proved NFAs are in fact equal to DFAs. But it's still useful sometimes to write an NFA because like it's efficient in programming. It's like we can be lazy and skip some stuff, implicit rejection and so on, right? But mathematically they do the same thing. But let's say you were counting complexity of state space or something. One may be, we know that there are languages that require large NFAs, require large DFAs but have small NFAs. So like we could say like efficiency-wise, DFAs are worse. Things like this could be said. But mathematically they're equivalent. So here mathematically they're equivalent in the sense that there's a polytime algorithm for one, a polytime non-deterministic algorithm for one, if and only if there's a polytime deterministic verifier for the other. But like conventionally, sometimes in a proof we need a definition of NP. We have the option now. Because sometimes it's easier to say, just guess this. Or we may want to use a verifier definition. So we say, well, okay, fine, the verifier definition is better here, so let's verify.
so either we guess it or someone already guessed it.
Yes, so that's a very important thing to note is that we have no idea how X was obtained. And in fact, part of the whole P versus NP question is like, it should take exponential time to find this X. But if someone did find the X, don't ask how, but if someone did find the X, we could verify it. The verifier you should think of does not have to find X, it's given X. Someone else did a lot of work for it. We're not gonna do the work, we're simply checking it. But to turn the verifier into an algorithm requires solving for X. That's bad, that's exponential time. Okay, pop quiz. Using both definitions of NP, why is P a subset of NP? Let's do the non-determinism definition first. Why is P a subset of NP? We're doing an easy direction, the easy part of a very, very hard problem. A very, very, very hard problem, but this is easy to show. Why is P a subset of NP?
It can be, if P, if the problem isn't P, it's simulated on a DTM, but any DTM can also be simulated on an NTM, it's just without the non-determinism aspect.
Perfect. Every DFA is an NFA. Same thing, right? Just by the generalization of non-determinism, every deterministic Turing machine is a non-deterministic Turing machine that doesn't use non-determinism. So just kind of trivially, we get this for free. In fact, it's true for any time class, n time f of n contains time f of n, right? Second, what if we use the verifier definition? Why is P a subset of NPV?
Because it's deterministic, we know we know the witness, or we can come up with
Sure. What is the verifier? Let's see. Let's write this one a little out. Let L be in P. Give me a verifier W. What should our witness be? So there exists, let's say, algorithm. If L is in P, there exists an algorithm A such that A on W will accept and reject. Give me a verifier. A. Yeah, the verifier is just going to ignore its witness and just, so like imagine if the verifier is an autograder and if the problem is simple, it's not going to check the answer, it's just going to resolve the problem and check that, right? So the witness in practice should help us convince us of hard problems. But if we're trying to convince ourselves of easy problems, we don't need to verify anything, we can just solve. The problem's simple to solve it. If it's hard, use the verifier to solve it, to verify it.
So like if it's 2sat, which is NP, it would just be the formula. That would be the verifier?
The verifier is an algorithm that takes on input 2 strings and outputs a yes or a no. In the sense that
Okay.
if the witness does correctly correspond, So it doesn't have to like decide the problem. The witness does, the verifier does what it does, and we argue about its behavior on all possible x, right? So like, for example, the verifier for SAT plugs and chugs. We don't care if it accepts or rejects or anything. It'll reject if it's given the wrong witness. But if there exists a correct witness to give it, then it will accept, right? So you can take an autograder that has a solution, give it a problem that does have a solution, and then give it the wrong solution, and it will correctly reject. But as long as there exists a correct solution, we should accept. It'll accept on that other computation. Okay. Right, so these aren't the only complexity classes, right? There are some others. We can define, P-space is another common one. P-space to be the class of languages decidable in polynomial space. Space complexity is very difficult to formalize, and many people get this kind of funky because we're not measuring time and space. We're measuring just space. So what that means is sometimes there are trade-offs you can do where you can save a constant amount of space for exponential blow-up in the runtime. So would you want to save space at the cost of time? Definitely not. But because this isn't time and space, just space, it technically allows that. What would you conjecture about space, P space versus P time, P? Which one is contained in the other? So P and P space, one of them is a subset of the other. Which one goes here and which one goes here is what I'm asking.
I would say that time contains space.
So which one goes here?
P space.
Okay, and P goes here. Every single person, every semester has gotten this wrong. I got this wrong when I was first learning this. It's the other way. That's why I asked this. We'll talk about this for a second. So if an algorithm runs in polynomial time, it can touch at most first off, how do we measure space? This is problematic, okay? You could imagine there is an algorithm that gets stuck in infinite loops on some inputs, but uses only 3 cells of the tape. We do not assign such an algorithm a space bound. We say the algorithm must halt on all inputs. We wouldn't call that a constant space algorithm. So the algorithm, to be a P-space machine, must halt on all inputs, and the maximum number of cells it uses is a polynomial as a function of n on a second work tape. So it has an input tape and then it has a second work tape, and we only measure the second work tape. We don't measure the first tape. Right. If a machine is polynomial runtime, it can touch at most a polynomial number of cells. So every polynomial time, if a language can be decided in polynomial time, it can also be decided in polynomial space. Okay? But you could imagine there might be problems which take exponential time but polynomial space, in the sense that they use a lot of time, but they don't have to write many things down. Certain brute force search algorithms might use constant space. Think about it. So a language being in here means there is an algorithm for it that uses at most a polynomial number of cells of the tape, but it could use exponential time. If it uses polynomial space, it doesn't require that it uses polynomial time, but if it uses polynomial time, it must use polynomial space. This convention tripped me up the first time, it trips everyone up. The other way around sounds better, right? What about NP? NP and P space. Which one goes here, which one goes here?
P space is a subset of NP.
I've never heard anyone get that one wrong, but that's actually the other way around. It's actually true that NP is a subset of P space. Why would you say, I'm just curious, why would you say that P space is a subset of NP? I want to know the intuition. There is intuition why P space should be a subset of P, because that sounds right. But why would you say P space is a subset of NP? Just curious.
I might have the wrong interpretation of what P space is, I think.
When we say P space is a subset of NP, it's not, but if we were to say that, what that would mean is if an algorithm runs perhaps in exponential time and polynomial space, then it can be verified in polynomial time, right? Which we don't know if it's true. We don't know if it's true or not. But we know the other direction, at least. We can't say if any of these containments are strict, by the way, right? Because if you can prove this is strict, you would win $1 million. We can't prove it's strict yet. we can say that NP is a subset of P space for two reasons. One, this is deterministic, by the way. So we could simulate the non-deterministic machine deterministically. Recall that had an exponential blow up in time. How much space did that simulation use though?
Polynomial space.
Yeah. So deterministically simulate the NTM. The NTM using polynomial time must use polynomial space. Your simulation won't keep more than a configuration on the tape. Therefore, well, a polynomial number of configurations, each polynomial size on the tape. So the simulation, without getting too precise in it, actually can be done in P space. There's actually three good reasons for this. Another one is like SAT is NP complete, and where you can put SAT, you can put any other problem. Turns out SAT can be done in P space. We'll talk about that later. Okay, let's use the verifier definition. Why is NPV in P space?
It still takes.
So give me a deterministic algorithm first, and we'll analyze its space. So give me an algorithm that runs in polynomial space, runs in quote unquote, uses polynomial space, but is deterministic. I guess what I'm saying is, the algorithm could look like this. So let this be the algorithm on input W. It's going to brute force for x and then run v on wx, right? If x is size n to the k, how many witnesses are there? How many strings are of that length?
Finite amount.
Well, for each n, sure, certainly, but as a function of n, where each witness is a bit string.
2 to the n.
2 to the n to the k.
To the
Right. Yeah, so that's exponential time. So for each of these, you run this verifier to see if any of them accept. But every time you use a witness, you erase it and write down the next one. So because you can reuse the space used is no more than the size of the witness, plus whatever this runs in, which is polynomial space as well. That'll take polynomial space. Okay? We'll talk about P space later. I think this is too early for P space. Let L, I'll do one more. Let L be the class of languages which is decidable in logarithmic space. Now, how do you talk about logarithmic space when the input is size n? You have a machine that has a second tape only for work, and the first tape is only for input. We count the number of bits used only on the second tape. What can you do in logarithmic space? Not much, but simultaneously quite a lot. To some people, logarithmic space is a much better definition of efficient algorithm than P, because what can you really do in logarithmic space? The only thing you can really do is keep counters on for loops. That's it. In P, you can do that, but then you can also do things like dynamic programming. So in some sense, to some people, I'll just go ahead and spoil it for you. L is known to be contained in P, okay? To some people, the question of L versus P is also unsolved. And not to some people, to everyone, but this question can be interpreted as, does dynamic programming do anything? Can you always undynamic programming any algorithm? If you have an efficient dynamic programming algorithm for a problem, is it true that you can solve the same problem without dynamic programming? That's what the question is, okay? So we are really good about comparing, so I'm mentioning unsolved problems. We can actually, is it this one? We can actually easily separate complexity classes in the case that they have the same resource. So what I've just said today is that L is a subset of P, which is a subset of NP, which is a subset of P space, right? If two classes are of the same resource, we don't know any of these to be equal. We don't know if P equals NP, we don't know if L equals P, and we certainly don't know if NP equals P space. So these are all open questions. But in fact, they're all related. We do know one thing. We do know that L does not equal P space. Why? Both of those are space complexity classes. So when two classes are of the same resource, it's actually kind of easy to show, and we'll prove it. It's called the hierarchy theorems. More time is more power, more space is more power. The proofs are actually by diagonalization. We'll prove it later. But we can actually prove that. So if we have a chain of set containments this way, and we know the left and right are not equal, what do we know?
P and NP have to be between them.
Yes. But specifically, give me something more specific.
If L doesn't equal P space, then L can't equal P.
I'll write it out. I'll write out another step. Suppose L does equal P, okay? And suppose dynamic programming doesn't do anything. Further suppose that all P space computation is verifiable. All polynomial space P space is verifiable. What should that imply?
P does not equal NP.
Correct. The answer I was looking for is that one of the containments was strict. If you have three containments, they can't all be equal. So at least one of them is not equal. We don't know which one, right? So you can actually prove the P versus NP question, which is a problem about space, which is not a problem about space complexity. It's a problem about non-determinism. You can prove P versus NP by proving questions about space complexity. If you can prove dynamic programming does nothing, and all polynomial space computation is verifiable to space complexity questions, you can prove the P versus NP question for free. So the P versus NP question, part of its lore is not that it is one problem, but is in fact 10,000 problems connected through perhaps one-way implications. So many things accidentally could imply one solution or the other, right? Similarly, if let X be the class of languages decidable in k equals 0 to infinity of time 2 to the n to the k. So it's not linear exponent exponential time, and in fact this is a class we won't use often, but you could say E is time 2 to the Cn for all C. We'll say 2 to the big O of n. So linear exponent would be called E, but if we allow a polynomial exponent, that's exponential time, right? So 2 to the n to the k. The reason we define exponential time this way as this way and not that way is because that's closed under composition and things like this, right? You can multiply two exponential time algorithms and you'll get exponential time. Closure. What is the relationship between NP? First off, what is the relationship between P and XP?
P is a subset of
Yeah.
XP?
Why?
Polynomial time grows smaller than exponential?
Big O properties, yeah. Okay, sounds fine. NP and XP, which one goes here? Which one goes here? This is also a tough one. And again, I'm asking you to compare and juggle resource. One is polynomial verifiable, one is exponential time. Exponential time, by the way, allows brute force.
NP is contained by EXP
Correct, why?
because it's the left is polynomial time and the right is exponential time.
Yeah, but this is non-deterministic polynomial time, so it's a little funny. It's a little funnier.
It can be simulated in exponential time.
Here's two answers. First off, using the non-deterministic definition, simulate that deterministically with exponential time. Recall that we mentioned that if an NTM runs in f of n time, the deterministic simulator for it runs in 2 to the f of n time. So if this is a polynomial NTM, this is n to the k, this is 2 to the n to the k, right? The BFS Turing machine that's deterministically simulating the non-deterministic one took exponential time, right? So that's true. What about the verifier definition? You brute force search for x takes 2 to the n to the k time. Forget the polynomial space part, just that long at least. That still works, so this is true for both, right? We know then that P is a subset of NP, which is a subset of XP. But like we know that L is not P space, we also can prove that P does not equal XP. We can, surprising to prove that, you may not believe that, but we can actually prove that. It's gonna be proven by diagonalization, create an exponential time algorithm, whose whole job is to be different than every polynomial time algorithm. We'll show you how to do that later, but this can be proven. So what does this tell you? Suppose that computation, all exponential time computation is verifiable. What does that imply?
P is not equal to NP.
So if you can verify all exponential time computation, P does not equal NP. The question about the P versus NP problem is not one question. Again, 10,000 accidental questions. So it implicates so much, and there's overwhelming evidence that the theorem is true. We have no idea how to prove it. Another one, a classic one, is like hash functions only exist if and only if P does not equal NP. Yeah, but we use hash functions all the time. Cryptography only works if P does not equal NP. So we assume P does not equal NP, and then just kind of hope it works. The whole internet is secured by the fact that P does not equal NP. What do I mean by the hash functions exist? I mean they provably have those properties. Like you can demonstrate a mathematical proof that they have those properties. They have observed statistical properties, and they look pretty random, and engineers are like, yeah, this is really hard to invert, and it has collision resistance. I mean, we ran it out of the computer for 20 days, and we couldn't find a collision, so it's probably collision resistant. But we can't ever, mathematically prove a function has those properties. So there are many intricate connections that tie in through many different fields. Right. Let co-NP be the class of languages such that L is in co-NP if and only if L complement is in NP. Another definition of co-NP could be that it is the opposite of an NP problem, right? What is the relationship between P and co-NP? Actually, I'll ask you another one. Why is P contained in co-NP?
Because P is in NP?
Yeah, basically, yeah. So we know P is in NP. And we know that if L is in P, that implies that L complement is in P. So we know that if L is in P, that implies that L complement is in NP, which implies that L is in co-NP. Something like this, okay? To give you a map of the world, here's P, here's NP, here's co-NP. Why do we care about co-NP? NP is the class of problems that have short proofs, as in the sense that you can convince someone quite quickly of a problem, okay? Co-NP is the class of problems that have short refutations, where it is the case that NP is the complement of the elements of co-NP, right, fine. But it is the case that you can quickly convince someone an answer is false, then it is, that kind of problem is in NP. For example, we know SAT, we won't define SAT exactly right now, but we know that, you may remember some of this. A logical formula is satisfiable if there exists a satisfying assignment, right? You can convince someone that there is a way to plug and chug an assignment into those variables such that it gives you a true at the end, right? So what we're really asking, in some sense, is in the truth table, does there exist a 1 here, right? That's when a formula is satisfiable, if there exists a 1 in its truth table. The witness is, which row is this? Because this is the answer. That is the witness. You plug and chug that. What is this would be the problem of SAT, right? We'll talk about this again on Monday. The problem of SAT complement is what? We ask for logical formulas such that there does not exist a satisfying assignment. So if there does not exist a satisfying assignment, what we're saying is that no assignment is satisfying. So these are all zeros, right? How can you quickly convince someone? I want to argue first, why should SAT complement not be in NP? Can you efficiently convince someone that a formula is unsatisfiable? What's your witness? You can't just give them all rows of the truth table because there's x2 to the n of them. If you have n variables, there's 2 to the n rows, so that's not a short answer. You cannot quickly convince someone that a formula is unsatisfiable, even though you can quickly convince someone that a formula is satisfiable. So there's an imbalance there. The second thing to note is, although SAT complement is not in NP probably, it is definitely in co-NP, simply by the definition of co-NP, but also it has a short refutation. Suppose I tell you a formula is unsatisfiable. You can quickly give me an efficient counterexample. How so?
Provide a satisfying witness.
Yeah, if you give the satisfying assignment, that means that is not unsatisfiable. That can refute SAT complement quickly, okay? So while SAT is probably NP, it is not probably, it is NP complete. Co-NP is, SAT complement is co-NP complete, right? So I gave you kind of a high-level reasoning about why SAT complement probably should not be in NP. Because it's like, what would the short witness be? But we also can't necessarily prove it. Just a poll for the audience. Do we think co-NP equals NP?
No.
What is your intuition?
Because if they were equal, then this is a leap, but then we know if NP is equal to P.
Basically. First off, to note the picture correctness. P is contained in NP. P is also contained in co-NP. So it is contained in the intersection. We'll talk about the strictness of this later. Is NP intersect co-NP equal to P? We'll talk about that in a second. But right now I can prove to you that if NP does not equal co-NP, that implies P does not equal NP. So the question is, not even about P. If you can prove that NP is not closed under complement, that's enough for you to prove P does not equal NP. Let's take a second to think about it. What could the proof look like? It's actually almost one sentence.
Something exists in NP that is not in co-NP?
It's simpler than that. That is a good first start. But the actual answer will be surprising. I'll tell you guys, if NP does not equal co-NP, we know that NP is not closed under complement. What is co-P?
The same as P.
P is closed under complement. So, if NP is not closed under complement, but P is, then P is closed under complement, NP is not closed under complement, so they can't be equal. Because if they were the same, they would both be closed under complement or both not closed under complement. But one is closed under complement and the other is not. So they have to be different. That's the answer, right? So the question is are these two equal or not? If they're not equal, then P is not equal to NP as well, okay? The next question is we know for certain that P is contained in NP intersect co-NP. That's not up for discussion. That's like, I mean, it's up for discussion. It's not like it's solved. I mean, we know that for certain. It's in here somewhere. But the question is it equal? When we did the chart, remember we did the recognizable and decidable languages. It was equal, in fact, right? We said that the intersection of the recognizable with the co-recognizable was in fact just the decidable languages. And in the analogous sense, you would think that to be true, but there is evidence that it is not. I'll give you some evidence. Suppose I ask you about the question about primes. Let primes be this language of binary encodings of numbers. Consider the language of primes. Do we think primes is in NP? Let's ask an easier question. Is primes in co-NP?
find a factor of, if you can.
Find a factor? That's a great idea. What's the complement of primes?
Composite?
Yes. So can you, instead of asking is primes in NP, let's ask, instead of asking if primes is in co-NP, let's ask is composites in NP. Can you quickly verify that a number is composite?
Yes.
What's the witness?
The factorization.
Yeah, or even a single factor. But the factorization would convince someone that a number is composite. So we know, for example, that composites is in NP. Now there's a result from the 70s that actually proves primes is also in NP. So primes is in NP and composites is in NP. That means they're both in NP intersect co-NP. So they were here for like 70 years. No, not 70 years, like 50 years. Prime and then not prime, okay? So that was our only example of a problem that was in NP intersect co-NP for a very long time. Well, the only easy one. Then, you won't believe this, in 2004, AKS 04 came out and it gave a deterministic primality testing algorithm, moving these into P. So we don't have that example anymore. The AKS result was basically a core tick time algorithm that like de-randomized something. By the way, we know, what do you guys know about primality testing algorithms?
Most of them use some degree of randomness, at
Yeah.
least the faster ones.
Exactly. Rabin-Miller uses random bits, and in fact, it can be de-randomized if and only if the Riemann hypothesis, something like this. And it also is not perfect, because it fails on Carmichael numbers. So it's an approximate randomized algorithm. That's not what P is. There's other classes called BPP, and ZPP and things like this that are attempting to capture that notion of randomized approximation algorithms. P is supposed to be perfect algorithms, okay? Primes was known to be in there, but the best deterministic algorithms for them were at super polynomial, so like not so good. This algorithm is the best one that doesn't use randomness, so we moved it into here. We still have a few candidate problems that are in NP, also in co-NP, but probably not in P. So we think this area is not empty. The two ones I know off the top of my head are like linear programming is one, because the duality theorem, if you remember the duality theorem from linear programming, every linear program has a dual and it's the same solution. So like the complement of a linear program is also a linear program, something like this basically. For that reason it can also be verified efficiently, but we don't know how to do it in polynomial time. That's an example, don't worry about that. Another one is like finding an equilibrium of a stochastic game. I'm not familiar with this at all, but that's like something I read. So some things appear there, but that are not in P. So we conjecture but cannot prove that this is hard. And in fact, I don't know it off the top of my head, but were you to prove that P is actually equal to NP intersect co-NP, that would probably collapse P and NP in some way. Again, 10,000 problems slightly related to each other through one-way implications and very difficult conjectures. But note that any kind of solution to one of them solves all of them in some sense, right? I'll give you one last one. Actually, I'll give you two last ones. We know that P is contained in NP, which is contained in P space, right? So there's an open question, is like P equal to P space? If that were true, what would that imply?
P is equal to NP?
Yeah. So some people are working, quote unquote, working on the P, no one's working on anything, they can't. But is P equal to P space? Is as hard of a question to ask as, does P equal NP? But P in P space is a question devoid of the discussion of non-determinism. It's the question about deterministic algorithms. If you can do it in polynomial space, does that mean you can also always do it in polynomial time? A fully deterministic question has an implication about a non-deterministic one, okay? The second thing I'll say is, actually, I have time, I'll do one more story. So there's this class known as BPP, okay? BPP stands for bounded error probabilistic polynomial time. Without getting too technical, imagine that there's an algorithm with access to randomness, as in the Turing machine has a second tape where someone has already filled it with coin flips. So it just reads bits off that. That abstracts us away from philosophical questions about what is randomness, because the machine is still deterministic, but the randomness is given to it, okay? it has bounded error in the sense that it can't make too many mistakes. It makes mistakes less than 1/3 of the time, or less than 1% of the time it's wrong, something like this. Is P contained in BPP or vice versa?
RZP is contained in BPP.
Correct. Okay. Every deterministic algorithm that makes no mistakes is also a randomized algorithm that does make mistakes. So, fine. Do we think, and I'm not asking for an answer, do we think that these are equal or not? Are randomized algorithms better?
There are randomized algorithms with better time complexities than non-randomized algorithms.
Fully agree, fully agree. Are they better over a polynomial? I think if you're a good algorithm designer, most people would say P probably does not equal BPP. That's, I think, very natural for you to say. In order for you to say P does not equal BPP, you must claim randomized algorithms are better. And that appears to be the case in the terms of what we experience. If you were to claim P does equal BPP, you are asserting every randomized algorithm can be de-randomized. It's hard to see how that could work necessarily. Okay. A second question, I promise this is related. Let E be the class, again, time of 2 to the O of n, okay? Linear exponent. Does E require 2 to the n sized circuits? We haven't talked about circuit complexity. But do we think that if you have a problem that can be solved by an exponential time algorithm, does the smallest circuit that solves the problem, we'll formalize that later, but just intuitively think about Boolean circuits that are hardware laid out in chips. Does the smallest Boolean circuit still have exponential size? How many people would agree or disagree with that?
I would agree.
Plausible. Why would you have a smaller circuit? By the way, if you have a circuit, you also have an algorithm, kind of. This algorithm just simulates the circuit, right? So, like, is that smaller than itself? Probably, I mean, no. So that sounds believable. Now, which would you believe more? This, do you believe more, or do you believe P does not equal BPP more?
I believe P is not equal BPP more.
Okay. Any others? The reason I mention this is a result from, I think, the year 2000. Aronson, it's Nissan and Wigderson, basically, no. Impliazzo and Wigderson prove that if E requires exponential sized circuits, then P equals BPP. I'm mentioning this because opinions by computer scientists can change over time. Many people conjectured P does not equal BPP, but they cannot prove it for the same reason we cannot prove P equals NP and so on. We just can't prove any of that, okay? By the way, BPP is in P space. So like P does not equal BPP would imply P does not equal P space, which would be great. We could solve the problem. So it's a hard question. Does randomized algorithms work? Most people would say yes. Randomized algorithms are far superior than non-randomized ones. In fact, until this 2004 result, the best algorithm that we had for primality testing was super polynomial. And then randomized ones were polynomial. So it appears like, oh wow, the primality is like definitely polynomial only if randomized, right? But this conjecture, I mean, this implication is like, if E requires exponential sized circuits, which is better, then P equals BPP. So basically what happened is there was a shift in opinion, it's a democratic institution. People now fully agree that it's probably the case that randomized algorithms don't do anything. P does equal BPP. And the proof basically involves of this hardness versus randomness paradigm where they have a general method to de-randomize something. Basically, any question you can ask about computer science can be formulated as a containment of complexity classes, and then that tells you the problem is basically impossible to solve. So we know that P is in BPP, which I will tell you for free is contained in P space. You just brute force search some stuff. So if you could prove P does not equal BPP, that would imply P does not equal to P space. So proving that randomness works is hard. Similarly, we can prove that P is in BQP, which is quantum polynomial time, which is contained, I think, in P space. I have to double check that. So if you can prove quantum computers actually work, you could also prove P does not equal P space. So you could also solve another problem. The relationship between BQP and NP is difficult, so I won't mention it. But basically, like, do these things work? We have no idea. And that's true for any possible problem you can ask. So the P versus NP question, actually nothing to do with P and NP. It's about randomness, it's about quantum computing, it's about space complexity, it's about hash functions, it's about cryptography, it's about proofs, it's about so many other things that are completely unrelated, but somehow, and that's kind of, I mentioned at the beginning that this is a horror. The theme should be horror, and it is horrifying because like we're really good at asking questions. We can't answer any of the questions, so we just like we ask questions with the hope to answer them. BPP was defined because it thought that P was too weak of a class, right? And then it turns out the P versus BPP question is hard because for the same reason the P versus P space question is hard. So questions get asked and they never get answered. We're having a bad time. Yeah. Question?
So why does, if P equals BPP, why does that imply that P does not equal P space?
No, the other way. If P does not equal BPP.
Oh, that, okay.
Yes. Now that is a one-way. There are, I think, fewer if and only ifs that I can think of, but there are definitely lots of P, if P then Qs. So if P does not equal BPP, right? If this is not this, and this is in this, then certainly this is not this. Same with here. If you can prove quantum computers actually speed something up, then you prove P does not equal P space. But we can't prove, we don't know how to prove P does not equal P space. So like, things are hard, basically. Not only are they hard, we'll talk about this much later on, like in a week or two. We can prove things are hard. So again, you cannot prove P versus NP, but in a meta sense, you can proving P versus NP is hard. And then there are even more recent papers that say something along the lines of proving P versus NP is hard to prove. So we're in meta levels that are, unlike in computability theory where we are confident that a problem is unsolvable, we're just saying that it's hard to prove something, which is different, because that's not even saying that it's unsolvable. Because if it was unsolvable, we could give up. Being hard doesn't mean someone else can't still do it. So that's the grand challenge in some sense. Questions? Next time we will talk very intimately about going on inside of the class NP.